Okay, in this chapter we'll talk about nucleophilic substitution and elimination reactions. Okay, so we'll use nucleophile to substitute groups on a molecule, or we'll use bases to remove or eliminate groups from a molecule. So elimination leads to formation of pi bonds. Substitution leads to formation of switched groups. Okay, so the groups will be switched, or elements will be switched or replaced. So a bond here is trying to lengthen and break and form with the other element. So this is just an animation showing you how you can break bonds when it gets longer, and how you can form bonds when an atom is next to another one. And this is just showing you a transition state where this group probably was here and this one is coming in. So we'll be discussing such things. Let's get in the chapter so that you can see what I mean. So let's start with nucleophilic substitution. You're gonna use a nucleophile to do the substitution. So there must be a leaving group. Someone has to leave, someone has to be substituted. The nucleophile does the attack. The one that's attacked is an electrophile. So this is an electrophile. The characteristic of electrophile is it should have a partially positive center or a fully positive center. The nucleophile will have lone pairs. Here it's positively charged, you have lone pair of electrons, you have negative charges, opposite charges attract. So we'll push the arrow from the lone pair, attacking the carbon bearing the partial positive charge. This leaves. Okay, so the leaving group left. So specifically, take OH to be your nucleophile. The oxygen has 3 lone pairs on it to make octet, including the 2 electrons in the bond. This is the carbon that's partially positive because chlorine pulls electrons towards itself. So use a lone pair to attack that carbon, and this leaves. Okay, now you get your alcohol, and then chloride becomes the leaving group. The reaction might go back, but in this case it won't, because alcohols contain OH, which is not a good leaving group to go the back way. So you will have substituted the chlorine with the OH, and you used a nucleophile, so that's nucleophilic substitution reaction. So nucleophiles generally will be electron rich, and they might be negatively charged, and they attack positive centers that we call electrophiles. Okay, nucleophiles can be neutral or negatively charged. Nucleophilicity is the ability of the nucleophile to attack. So that goes with how available the electrons are in the nucleophile. The more available the electrons, the more reactive the nucleophile. Okay, so it can be neutral, like in alkenes. Remember, we used alkenes to attack acids. Okay, so where we formed our carbocation, so probably this will be the carbocation to be formed. The CH2 turns to a CH3, and then the other CH2 will be a positive charge. So that's the carbocation as Br leaves. So here you're using the 2 electrons to attack the partially positive hydrogen, which is partially positive because bromine again is electronegative. So this is a neutral nucleophile. OH minus was a negatively charged nucleophile. OH minus is a negatively charged nucleophile. Ammonia is neutral nucleophile. So the nucleophiles can be negatively charged, neutral, as in, for example, ammonia or alkenes. You just have to have those electrons available to be used. Okay? So again, these are examples of neutral nucleophiles. These are examples of negatively charged nucleophiles, what we call anionic. Okay, so what makes a nucleophile strong? Factor number one is electronegativity. So let me write it here. Electronegativity. You know, that increases across the periodic table. So let's look at the second period. Fluorine will be the most electronegative, and fluorine will be the poorest nucleophile in this list. In principle, if an element holds on electrons strongly, which means increase in electronegativity, that will decrease nucleophilicity. Okay, so an element that's more electronegative would not be a good nucleophile. So that's why C minus will be a stronger nucleophile than M minus, than O minus, than F minus. Now, what if you have the same element bearing the lone pairs? For example, here the oxygen is bearing the lone pairs, the oxygen is bearing the lone pairs. The species that will have a high density of electrons will be a stronger nucleophile. Okay? And in fact, it turns out it's going to still be a stronger base. It's the same order for the base. So OH minus is a stronger nucleophile than water. NH2 minus is a stronger nucleophile than NH3. CH3 minus is a stronger nucleophile than CH4, just because of the high electron density, which brings the negative charge. Factor number 3 is polarization. We consider a group of the periodic table. So like in halogens, you have F, Cl, Br, and I. If these guys are anionic, right, which is what we want for nucleophiles, you have to consider size. Going down, the size increases. If the size increases, you're increasing polarizability. Okay? Increasing size increases polarizability. What do I mean by polarizability? So, you know, if you have the fluorine, which is small, it's just gonna be circular, and the electrons will stay in the circle, maintaining the shape. But for iodide, which is big, okay, the I minus, which is big, this was F minus. For I minus, which is big, these charges can be concentrated on one side. So assume it was spherical. This can change its shape to like a flat shape where the electrons will be concentrated on one side, the positive charge will be concentrated on the other side, and that's what's called polarization. You see, we have now polar ends. So because iodide is big, it can change its shape, and therefore you can imagine it's possible to attack this carbon center. So iodide can fit in that pocket to attack the carbon, partially positive carbon center in a substitution reaction. But F minus cannot conform its shape, cannot change its shape because it's small. So the bigger the anion, the better it can change its shape or change conformation, which creates polarization of the charges, which helps it to attack. Okay, but basicity will be opposite. For basicity, F minus will be more basic than I minus, because the electrons are readily available in the small size of the anion compared to where the anion is big and the electrons have much room. Alright, so you're shown here that these are very weak nucleophiles. Obviously, you see what they have in common is that they're neutral. But these ones, which are negatively charged, are usually good nucleophiles. We prefer them. Ammonia here is neutral, but it's listed on this row because nitrogen is less electronegative. It's generous to give its electrons. Alright, so you are shown examples of nucleophiles and their strengths. Let's talk about the leaving group. What makes a leaving group a good leaving group? Okay, so generally, if you have an acid, the acid can ionize. So for example, if you have HCl, the chlorine can fall off, you get a plus sign, and you get Cl minus, which means Cl left. Okay, so it's a leaving group. So that's with general chemistry. Okay, now in organic chemistry, where you have organic molecule, if you have a halogen like a Cl, the Cl can fall off to give you Cl minus, and you make a carbocation. Okay, so what helps these groups want to leave? What help the group want to leave? Okay, they should make a weak conjugate base. So that's factor number one, is basicity. You want it to be a weak base. And what makes a weak base? There are factors like electronegativity, resonance, and size. Okay, I'm trying to answer this question. What do you mean by this? A good leaving group can be recognized as being the conjugate base of a strong acid. So when a strong acid breaks down, you get a leaving group that will got what we call a conjugate base, and the conjugate base is stabilized, like I said, by electronegativity, size. The bigger the size, the better, and resonance. So let's look at these factors. So the factors that stabilize the conjugate base will make the leaving group a good leaving group. Okay, so let's see such factors. So now let's see such factors. So for example, if I'm to compare F minus and I minus, who's a good leaving group? So for example, let's say we had this and we had that. Who is the good leaving group? The better leaving group will be the I minus, the iodide, because once it leaves, it's gonna give you a carbocation and I minus. That's big. There's more volume, there's more room for electrons to stay. So I minus is a better leaving group than fluorine if fluorine were to leave, to give you F minus and the carbocation. So size plays a role here. Okay, so this will be the conjugate base. The I minus is the conjugate base. It was part of the original molecule, which will pretend it's an acid. So that's the conjugate base, stabilized by size. Now here, these are very poor leaving groups. So for example, let's say you have OH and you're pretending that the OH leaves to get the carbocation and OH minus. You know, hydroxides are strong bases. We said the conjugate base must be a weak base, not a strong base. So the same thing applies. If you have an ether, you get a plus sign, you get OCH3 minus. This is an example of OR minus. That's still a strong base. I would rather have the OH leave in form of water. So let's say you have this organic molecule. When the left part leaves, you get a carbocation and H2O. You see, water is neutral. OH minus, which is part of the formula of water, is negatively charged and a strong base, but water is neutral. If water was a strong base, we'll all be dead, because we drink it all the time. Now for ammonia to leave, the nitrogen is gonna be a plus charge. So if that falls off, you get a plus sign and you get ammonia. Again, ammonia is neutral. Compare that with NH2. If NH2 were to leave, you'll get your carbocation and you'll get NH2 minus. You get NH2 minus. Okay, this is a strong base. So strong bases are not good. See, NH2 minus is not a good leaving group because all these are strong bases. So you want weak bases. on neutral. That's what you have here. Okay. The plus charge on oxygen and nitrogen makes water and ammonia very good living groups. And I talked about iodide, I said that's because of size. Now, let's talk about the rate of reaction and the mechanism. So remember, OH minus is a nucleophile. Use the lone pair on oxygen to attack the partially positive carbon. Again, this is partially positive because bromine attracts electrons towards itself. So you'll attack this carbon and this leaves. So you get an alcohol from an alkyl halide. Halide halogen, alkyl group. So again, the reaction happens by back attack. Now, it's well seen if we draw the hydrogens on the back side and show that yes, the OH is not obstructed by anything. It's just gonna go in there to attack because the hydrogens are small. They don't crowd on the back side, right? And that's one thing with SN2, because this is SN2. SN2 doesn't like sterics on the back side. I'll emphasize that each time. So this reaction is concerted. It happens at once. Okay, it's one step. Now, notice that because it's one step, then the nucleophile and the electrophile, this is an electrophile because there's an element which is bearing the plus character. The nucleophile and the electrophile are working together. So that's why it's SN2. Two things determine the rate. Rate determining step is the reaction of these two guys. So in fact, if you look at the rate equation, the brackets imply the concentration. In the rate equation, the concentration of the electrophile and the nucleophile must be considered. The concentration of the electrophile and the nucleophile must be considered. K here is just a rate constant that must be determined in the lab. We don't know what that number is. So in SN2 reactions, two species are used at once in the very first reaction mechanism. So it's bimolecular. So two molecules determine the rate, and their concentrations will determine the rate. This is the rate constant. So now, if you double the concentration of the electrophile, the rate will double because the electrophile is part of the first step. If you double the concentration of the nucleophile, the rate will double. Now, what if you double in SN2? What if you double the concentration of both the electrophile and the concentration of the nucleophile? The rate will increase by a factor of 4, so we usually say that the rate will quadruple. That is with SN2. SN2 will not happen here. Here SN1 will happen. Why? Why the difference? The reason is the structure of the electrophile. Remember how we said that here we are doing a back attack, all because the backside is accessible, and that's what you want for SN2. Can we do a back attack on this electrophile where you have the methyl groups at the back? The answer is no. You cannot do that. If the nucleophile tries to come to approach the partially positive carbon, like in this manner, it's not going to work because the CH3s are crowding the backside. Now, for this reaction to happen, the leaving group has to go first. Okay? So the leaving group has to fall out first, and that's going to be the rate determining step. Guess what you'll form? You get a carbocation. You know, these are CH3s. I don't have to keep drawing them. I don't need to write CH3s all the time. You get a carbocation, you get bromine that left. Remember, we said that the carbocation centers are sp2 hybridized, so this carbocation, the carbocation is trigonal and planar, so the molecule is flat like sitting on the bench of your table. So now the OH can now come later on in the second step. That's when the OH will come back to attack the carbocation, either from the left or from the right, from the top or from the bottom. The point is now this C plus is accessible. Here it was not accessible, here it's now accessible. So only one thing determines the rate. That's why SN1 is unimolecular. The electrophile determines the rate. You have to form the carbocation first before the nucleophile attacks to give you the alcohol. Because once OH attacks, you get the alcohol. So one thing determines the rate. So this reaction is called unimolecular. Why? Because one species determines the rate. Unimolecular nucleophilic substitution. That's how you get your alcohol. This alcohol is this alcohol right here. These are the 3 CH3s in parentheses. The beer fell off here. So one thing determines the rate. It's unimolecular. Here it's bimolecular because two things determine the rate. Now, if you increase the concentration of the nucleophile, which means you increase the concentration of OH minus, there's gonna be no effect on the rate. No effect on the rate of reaction. Why? The OH was used in the second step, not the first step. And in fact, the OH is not part of the formula here. Only the concentration of the electrophile. Okay, but if you double the concentration of the electrophile, the rate has to double. Okay, so doubling the concentration of this electrophile will double the rate. Tripling will triple the rate because it's part of the formula for SN1. So let's discuss SN2. I'm now going to break down SN2 and SN1. I'm starting with SN2. I've already given you the overview in this slide. So I'll repeat myself. First rule, there's going to be a back attack of the nucleophile. Okay? Back attack of the nucleophile. So the nucleophile approaches the electrophile from the back side as the leaving group goes. Okay? The two molecules are involved in the rate determining step. So the rate formula will involve both the alkyl halide and the nucleophile, the electrophile and the nucleophile. So the reaction here is bimolecular. Bimolecular nucleophilic substitution. Two molecules determine the rate. And it's one step. So it's back attack and it's going to be concerted. One step reaction, one step reaction. And then the other one, because of the back attack, we expect there's going to be inversion of configuration. We'll talk about that later. And then, of course, in all these reactions, there's going to be a transition state. So the oxygen will want to make a bond with the carbon as this bond wants to break. So you get a transition state. Okay? You get a transition state. So this bond right here wants to form. So it's forming. And this bond right here wants to break. So it's breaking. Once this breaks, you get the leaving group. And then once this forms, you get the alcohol. So this animation is showing you the OH approaching with 3 lone pairs. 1 lone pair will stretch to attack the carbon. We want to form that bond as this bond wants to break. And if this was Br, it falls off. So again, you have the hydrogen and oxygen with 3 lone pairs. 1 lone pair will come to attack. You get a transition state. That bond forms, this breaks. Now I want you to pay attention on the configuration of the starting material. You see how these three groups are on the left. Once you attack, they will be on the plane, and then now they are on the right. That's what we call inversion of configuration that I want to talk about. Okay, so I hope that animation helped. Now, in terms of the energy diagram, the transition state will be up here. These are your reactants, the alcohol and the alkyl halide, and these are your products. Okay, you get your alcohol. Now, because the nucleophile attacks from the back, we say that the backside should be much accessible. So I would expect that where you have all CH3s with the leaving group X, this one will be more reactive than where you have a CH2 with one R group, carbon containing group. This is called primary because there's one R group, which will be more reactive than a secondary alkyl halide, because now you're introducing sterics or crowding on the backside, which will be more reactive than one that has 3 R groups. Okay, so specifically, I would say methyl bromide is more reactive than, let's say, ethyl bromide, which would be more reactive than isopropyl bromide. Which will be more reactive than tert-butyl-bromide. Why? Because the nucleophile will have a hard time, for example here, attacking this carbon right there because of crowding on the backside. So this is methyl. This is called methyl halide. This is primary because it's one R group. This is secondary because there are 2 R groups, and this is tertiary because there are 3 R groups. So that's the trend for SN2. The trend for SN2, methyl X is more reactive than primary, primary is more reactive than secondary, secondary is more reactive than tertiary. We are just focusing on the structure of the electrophile. Okay? There's gonna be inversion of configuration. I already talked about that in the animation. All right. So for SN1, this will be opposite. SN1 will prefer tertiary over secondary and over primary over methyl X, because that goes with stability of the carbocation. Remember, we said only the electrophile determines the rate, because this nucleophile has no chance to attack the carbon in the middle. We said because of crowding, you cannot do SN2. Instead, you do SN1. For SN1, the rate determining step is formation of a carbocation. So when that falls off, you get a carbocation, which is simply this molecule right here. Only then will the nucleophile come to attack to get the alcohol. So formation of the carbocation intermediate is the rate determining step. Okay, this is the rate determining step. First, you form the carbocation before the nucleophile comes to attack. Okay, and that's why only one molecule determines the rate, which is this substrate, and that's why it's called SN1, because one molecule determines the rate. It's unimolecular, but you're still substituting because the Br will be swapped with OH. Okay, the loss of the leaving group helps you to make the carbocation. When Br falls off, you make your carbocation, this one, which is just this. Notice it's drawn like in one line because you have 3 electron groups around the carbon. So it's sp2 hybridized, it's trigonal and planar. So it's flat. And the nucleophile can attack either from the left or the right to get your product. So let's talk about the transition state. So first, the rate determining step is formation of carbocation. So the transition state here will be where you want the bromine to break off. So that will be the transition state. Once the bromine breaks off, you get your carbocation, which without showing the hydrogens, which will look like that. So this is simply what I've drawn here. And then now, from there, your nucleophile, in this case, your nucleophile is water. Your nucleophile can now come to attack. So the nucleophile is water. So it will want to form a bond with the positive center. That gives you the second transition state. Okay. The water wants to form a bond. Once it forms a bond, which is this bond, you get this product. This product is simply this structure with the water with the plus sign on the oxygen. And then usually you don't want the extra hydrogen, so you have to take out the extra hydrogen. So to take out the extra hydrogen, you're gonna use a base. You get another transition state where the base will want to pull off the extra hydrogen and this bond will want to break. Okay, so this will be the next transition state. Once the extra hydrogen is taken out, you're left with the OH, which is this product right here. So you see, the key point here is not you trying to identify the transition states. The key point is SN1 will go through multiple transition states. There's a transition state here, transition state here, and transition state here. Compare that to SN1, there's only one transition state. That's why SN1 was said to be concerted. That's the key point I want you to understand. SN1 will go through multiple transition states. It's not concerted, but SN2 is concerted. Only one transition state. Okay. So next time we'll continue and talk about stereochemistry.